Hi, so in this video I'm going to talk to you about what to do when you have an improper fraction. Okay, this is an improper fraction. First of all, let's just discuss that. What actually is an improper fraction? Well, in terms of numbers, I'm sure if I wrote down 7/4, you would tell me that's an improper fraction or top-heavy fraction, because immediately you say, well, the numerator is larger than the denominator. Okay, but what about this one? What if we had 4/4? That's also an improper fraction. Okay, it's like you probably didn't really think about it until now, until I just posed the question, because 4/4 you just normally write as 1, wouldn't you? Okay, but the fact of the matter is that is an improper fraction. In terms of algebra, okay, what makes an improper fraction is if the numerator is the same or greater than the power of the denominator. I didn't say that particularly well, so let me do it again, okay? So the numerator, okay, that's a linear term. The denominator, that's also a linear term. Linear over linear makes a improper fraction. Or a quadratic over linear makes an improper fraction. Or a cubic over linear makes an improper fraction. What you're looking at is the greatest power term, sometimes called the order, okay? The greatest power term on the top, if that is the same as or greater than the highest power term on the denominator, then it's an improper fraction. Okay, you need to be able to see those, because if you express those as partial fractions, then there's a slightly different technique required. Okay, you don't just start straight away with the a over whatever. Okay, because if you think about it, well, what are you going to write? You just copy x plus 1. No, what you've got to do is consider what would happen if you divided a linear algebra expression by another linear algebra expression. Okay, well, you'd get a numerical value, wouldn't you? Okay, you'd get a numerical value. Let's call it a, and there'd be some remainder. Okay, some remainder is also a numerical value. Let's call that remainder b. And what would you do? You'd write that remainder as a fraction over the original divisor. Okay, so that's how you set out your partial fraction. Okay, and then you solve it in the same way as you were before. So let's just multiply both sides by x plus 1. Let's put the identity symbol in there for completeness, like I have been doing in the previous videos. Multiply both sides by x plus 1. On the left you have 2x, and on the right you'd have a x plus 1 plus b, and then you just solve it as you would do before. So let's try x equals -1. On the left you get -2 is equal to b. It's quite simple, so b is -2, and let's just put in x equals 0, shall we? On the left you'd get 0, and on the right you'd get 1a plus b, so you get a is equal to -b, so that's got to be a is equal to 2. Okay, and therefore the partial fractions are going to be 2 subtract 2 over x plus 1. Okay, 2 subtract 2 over x plus 1. Okay, done. Now I'm going to show you an alternative method to doing this, one that will get you the answer without even considering partial fractions. Okay, let me show you. Do you remember a while ago you learned how to use long division? Okay, well, this is something you can also do. Okay, long division, 2x over x plus 1. So set out we're working like this. So 2x divided by x plus 1. Okay, so x into 2x goes twice, so let's put it there, and then 2 times x plus 1 is 2x plus 2. Find the difference, 0. Of course that's a 0 as well. 0 subtract 2, -2, so you got 2, remainder -2. How do you write that answer? You write your answer as 2, there it is, and the remainder you write as a fraction of the original divisor. Okay, so subtract 2 over x plus 1. Okay, that's how I would do it, it's just slightly quicker that way. Okay, there's another example coming right up. Okay, next example then, using improper fractions. This you can see quite clearly, again, an improper fraction. You've got a cubic on the numerator and a quadratic on the denominator. Cubic over quadratic is going to be an improper fraction, okay? So let's think about what you'd get if you did a long division. I'm going to do that in a minute, by the way. If you did a long division on this, what would you get? Well, a cubic divided by a quadratic is a linear, isn't it? Okay, so you'd expect to get some sort of linear answer. So that would be ax plus b as your typical linear answer. And then you'd have some sort of remainder. Okay, and the remainder then you put over the original divisor. Okay, now when you split those up into partial fractions, you're going to have c over x minus 1, and then you have d over x minus 2. Okay, and then you you can solve it that way. The next step will be to multiply both sides by the denominator and then work at a, b, c, d. Okay. I've got a slightly different way, a preferred way that I'm going to show you using long division. Okay, just that I don't fancy working out a, b, c, and d. It's just too much stuff there. Okay, so I'm not going to bother with that approach. Okay, what I'm going to do, I'm going to go straight into long division. Okay, so let's see. We're going to have 3x cubed divided by that. So in the long division, I'm going to have to expand the brackets there really. X squared subtract 3x plus 2. And then I'm going to have 3x cubed. And of course I better fill in the 0x squared plus 0x plus 0. Okay? And then start the long division process. So x squared times 3x gives me that. So 3x will go there. 3x times all of this will give me 3x cubed. Subtract 9x squared plus 6x. Find the difference. So 0, that would be 9x squared, subtract 6x, and then start again. X squared times 9 gives me 9x squared, so that could be plus 9 there. And then 9 times all of that, so 9x squared, subtract 27x plus 18. Let's just put in plus 0 there, shall we? Find the difference between that, 0, and then negative 6 plus 27, so 27 subtract 6, 21x, and then subtract 18, okay? So my answer is going to be, let's write it up here, that divided by that is 3x plus 9 with a remainder of that, and the remainder we shall write as 21x subtract 18 over x minus 1, x minus 2 over the original divisor, of course. Okay. So what that has enabled me to do is, in my opinion, rather quickly work out the value of a and b. Remember I had ax plus b there before? That long division process has quickly enabled me to find that a is 3 and b is 9. Okay. That's why I prefer it really. Because now all I need to do, free screen if you want, copy down. Okay, I'll rub it off because my job there is done with the long division. Now what I need to do is just find the partial fractions on that. Okay, so let's just write it down. So you've got 21x minus 18 over x minus 1, x minus 2. Okay, and the partial fractions will look like this: a over x minus 1 plus b over x minus 2. Apologies for earlier using a and b there, but in the context of my question, the way I'm doing it, that's the first time I'm writing the letters a and b, okay? Anyway, I prefer with partial fractions, to be honest, to use a and b like that. So what we're going to do, multiply both sides by x minus 1, x minus 2. So on the left we'll have 21x minus 18. On the right we'll have a x minus 2 plus b x minus 1. This is looking like a really easy one, isn't it? Because this is probably one, a bit like one of the really early ones in the unit. Okay, it's a simple one. Let's put in x is equal to 1 first. So we get 21 subtract 18, that's 3. And that's going to be equal to 1 subtract 2, negative a. So a is equal to negative 3. And then let's put in x is equal to 2. So here we get 42 subtract 18. So 42 subtract 18, 42, 32, 24 is equal to 2 subtract 1, 1b. So b is equal to 24. Okay. So our answer then is 3x plus 9. And then the partial fraction bit that I did. Subtract 3 over x minus 1 plus b 24 over x minus 2. Okay, and that's it. Job done. Job done. Hope you found that useful. Okay, I'll see you again. Okay, so my next example, clearly another top-heavy fraction, another improper fraction, okay? But let me show you a really nice, quick and simple method that you could use, okay? In an example like this, notice how similar the numerator and denominator are. X plus 1, x plus 2. Okay? All I need to do to make the numerator the same as the denominator is add on 1, don't I? Okay? So if I add on 1 to it, let's just extend the line there. If I add on 1, that becomes the same, okay? But of course, you're not just allowed to add on 1 for no reason, because that changes the whole question, doesn't it, okay? But what if I add on 1 and then subtract 1, okay? That is the same as 0, isn't it? Then the whole fraction stays the same. But what I've got now is, I've got x plus 2, subtract 1 on the numerator, and x plus 2 on the denominator, okay? And what I can now do is I can just rewrite it like this, x plus 2 over x plus 2, subtract 1 over x plus 2. Notice how that works? Because I've just taken that bit as being separate from that bit and written as that divided by x plus 2, subtract 1 over x plus 2. And of course, that divided by that is just 1, isn't it? Okay, you get 1, and then this is subtract 1 over x plus 2. And that's it, done. Okay, the answer's done. Didn't even need to think about partial fractions, didn't even need to consider long division. Okay, I call it the plus 1 minus 1 method, or some people might call it the plus 1 minus 1 trick. Okay, it's quite handy in a situation like that. So I thought I'd share that with you. Okay, I'll see you again.